Lesson 2 for atomic structure and periodicity. Here we go. First of all, we'll start with the wave mechanical model. This is our modern view of the atom at this time, and we visualize the electron as a standing wave instead of a traveling wave like a vibrating guitar string. Okay, so the shapes of these orbitals or sublevels, according to Schrodinger's equation, the wave function, which is a function of the x, y, and z coordinates, gives us these orbitals. And so we have S, P, D, and F. In Chem 1, we remember the order by science is pretty darn fun. You can come up with your own little saying if you want. But this is just showing you what their shapes look like as they rotate around the x, y, z axis. Each one of these shapes, if you will hold 2 electrons. And we have ways of designating that, which is electron address, which is quantum numbers. First of all, we need to talk about Heisenberg uncertainty principle, which basically says, hey, we can't know where the electron is and how fast it's going at the same time. Actually, for any particle, at any given time, we can't know both its location and its velocity at the same time. For really, really big objects, not that big of a deal, but for really small electrons, it becomes a big deal. So that means we know within a 90% probability of where that electron is located. Electron arrangement, of course, is we do it in a specific way so that we can be talking about the same electron across the board when we're referring to them. We have energy levels. The energy level does correspond with the period number on your periodic table. In the energy level, of course, the higher the energy level number, the larger the orbital is and the further away it is. And also it can hold more and more electrons. So the N1 doesn't hold only 2 electrons, that's all it can hold. But you get out to 4 and 5 and that can hold a lot more. So your energy sublevels are your SPD and your F sublevels, and they have corresponding orbitals, which corresponds to how many orientations around the XYZ axis they may have. So an S is 1, and it holds 2 electrons. Each orbital can only hold 2 electrons. The sublevel can hold more. For instance, a P has 3 orbitals, so that P sublevel can hold 6 electrons. The D can hold 10 with 5 orbitals, and the F can hold 14 electrons with 7 orbitals. The principal quantum numbers are the address of the electron. The first one is the principal quantum number, which tells you the energy level. And so you're not responsible for assigning quantum numbers any longer. I'm going to show you one example as we go through this, and I'm going to use the 3p3, like if we had electron configuration that ended in 3p3, and I wanted to know what the quantum number was for that last electron. So in this case, the principal quantum number is your energy level, so it's always the big number, so it's going to be 3. The angular momentum quantum number is telling you, are you in an S, P, D, or an F? And these numbers correspond to that. So we are, in fact, in a P, so we would say our second quantum number is a 1. So that tells us, hey, we're in a P orbital. And then the third quantum number is the magnetic quantum number, and it basically is telling you which one of those orbitals is it in. And since we're in a P, we're going to draw 3 lines to represent the 3 orbitals orientations. And so their values are negative L to positive L. Well, for L, up here, we wrote down 1. So that means we're going to go negative 1, 0, and 1. Okay? And then we see that we have 3 electrons, and so we're going to put in 3 electrons, 1, 2, 3. In a minute, I'll tell you why I put them all up if you don't remember. And so this last electron went right here. And so our second one would be, our third quantum number would be a 1 to tell us that we're in the 3rd slot. And then lastly, we have the spin quantum number, and it's going to tell us if that spin quantum number is going up or down. This is a half, and this is a negative half. And then so that last quantum number would be a negative half. Okay? If you didn't understand that, it's okay. You're not tested on it, but I did want to recall that from pre-AP Chem. And if you ever saw it, like maybe on an SAT subject test or something like that, at least you've seen it. The orbital shapes and their energies, there, of course, is the 90% region, and of course, in this case, it's the yellow and blue that we're seeing. But there are areas of 0 electron probability, and we call those nodes. And then orbitals that are equal energy, we say they're degenerate. And of course, that's going to be your P's, your F's, and your D's. And those slots or boxes that we draw to represent the orbitals orientation, they are all equal energy. So the 3 rules that govern how we do electron configuration, the first one is Pauli Exclusion principle, and it states that in a given atom, no 2 electrons can have the same set of quantum numbers, same 4 sets, okay? And that means basically that they have to have opposite spin. So we can't put them in together, going around the electron 2 by 2, like a Noah's Ark or anything, because there is great electron repulsion because they're the same charge, so they're going to be spinning in opposite directions. The Aufbau principle states that you must fill the lowest energy level first. Sometimes that is referred to the lazy tenant rule, because the lazy tenant wants to live on the bottom floor. This is the order that they fill. You do not need to memorize that because we fill them directly off of the periodic table because of the way it's arranged. And then the last rule is Hunds Rule, or the empty bus seat rule, but it's basically saying everybody's got to get an up electron before you give it a second electron. So you can't, like the first one is wrong because you have 4 electrons, you can't just pair them up 2 by 2. You got to give everybody an up arrow or a parallel spin before you give them the opposite spin. All right, so here is our periodic table. Just recalling of how we read this, our they have the S block, the P block, the D block, and the F block. Those blocks do correspond with how many electrons each one of those blocks can hold, or those sublevels can hold. So a P can hold 3 sublevels for a total of 6 electrons. So if you count that up, there are 6 groups. In the P block, an S holds 2 electrons in 1 orbital, 2 groups, etc. Okay? So exceptions to Aufbau principle. In pre-AP, we learned copper and chromium. We also did molybdenum, silver, and gold. And the good news is you are not responsible for those any longer on the AP exam. However, you do need to be able to, if they asked you a question about, like, it's this instead of that, why? And you would want to say this, because fewer electrons are sharing orbitals, electron repulsion is decreased and stability is increased. So that's what you would want to say there. You would, if I doubt that they would actually ask you to do an electron configuration on one of the exceptions. If they're going to ask you a question about it, it's going to be, hey, just like this one right here, hey, we expected it to be 4s2, 3d9, but experimentally we find it to be the s1d10. Why? And this is what you would say. Orbital notation, that's the way we draw the lines and arrows. So this one right here, we did 1s2, 2s2, 2p3, and if you look at 2p3, we could say, hey, that is nitrogen, because we know, also we could count up the electrons, 1, 2, 3, 4, 5, 6, 7. 7 electrons means it's nitrogen in this case, unless it was an ion. The standard or complete electron configuration is when you list out the whole thing. 1s2, 2s2, 2p3, again showing nitrogen. And then electron configuration with the noble gases is called the noble gas core method. Sometimes you might see it shorthand notation, but basically you will use the noble gas that's previous to whatever you're doing, and then follow what comes after that. So in this case, we're doing phosphorus. Phosphorus ends in 3p3, and so we look before phosphorus comes neon. And then neon ends in 2p6, so we would only need to list what comes after neon. Okay? So now let's get ready to practice this in a moment. Ions we'll do second. We're going to do regular ones first. But ions, basically, if they are gaining or losing, they're actually going to reach the same configuration as the noble gas that either comes before or after it. So we'll do that in a minute. But in each case, the electrons are removed from the outermost shell. Okay? Which is going to be weird, and because we fill them in a different order. But if you've got something in the D block, they will lose their outer S electron before the D. So it's not necessarily a last in, first out when you're talking about the D block. So we have to consider that when we're doing that. Okay, So here we have some electron configurations for the following. I'm going to do one or two of these, and then I'm going to probably do at least one of one that's not on here, because I want to do something that shows up, or I want to show you how to fill the F block, because it can be a little different. Okay, so I'm going to pull up the next slide so that we can refer back to this. So we are going to start with cobalt. And if we look where cobalt is, 1, 2, cobalt's right here. All right, and if we count, we want to see what it's going to end in, because that's the easiest thing to do, is just add these up and stop where you end. And so we are in 3D, and if I count over, that's 3D7. So we're simply just going to start filling up the chart and say, oh, I'm going to fill up 1s, so that holds 2 electrons. Then I'm going to go down here and I'm going to fill up 2s, holds 2 electrons. Keep going, I'm going to fill up 2p, which holds 6 electrons. 3s holds 2 electrons. 3p holds 6 electrons. 4s holds 2 electrons. And then 3d7. Now, in Chem 1, I made you just write it like this, the order that it fills. But in AP, I'm going to ask you to rearrange those in the order that they keep their energy levels together. So we would rewrite that as 1s2, 2s2, 2p6, 3s2, 3p6, 3, see out of habit, 3d7, and 4s2. And that shows you, because of that, that's where those valence electrons would be pulled from. Now, if I wanted to do the noble gas notation for this, I would find the noble gas that comes before cobalt, which is right here, argon. So then I would say argon, brackets, not parentheses. And we know that argon ends in 3p6, so that's essentially argon right there. And so we would write 3d7 4s2. Okay? If I was going to write, and this is the only one we'll do this on, if I was going to write the orbital diagram for the last valence electrons, so I would just do this. I would say 1, 2, 3, 4, 5 for 3d. And then 4s is down here. And then I have, at this point, 20 electrons, 18 electrons with argon. So then I would go 19, 20, 21, 22, 23, 24, 25, 26, 27. So that would be its outer configuration. Okay? If for fun I was going to do the quantum numbers, I would say 3, 2 for D. It's in the second slot, so -2, -1, be -1, spinning down, -half. Okay, so let's do another one. Let's go ahead on your chart. Let's erase all that. And on your chart, let's do, let's do gallium. Gallium is right here. And so that's going to end in 4p1. And so we're going to start, again, filling up the 1s's, 1s2, filling up 2s, 2s2, 2p6, 3s2, 3p6. Now I know I'm going to come down here, so to save myself time, I'm going to go ahead and do 3d10, then 4s2, 4p1. So I'm just saving myself time. You don't have to do that. You can do the order that it fills, and then rearrange it if you would like. And then, of course, the noble gas, we're still dealing with argon right here. So it'd be argon, 3d10, 4s2, 4p1. Okay? So I want to show you something for the F block on this next part, which is not in your notes, but I believe there's some room down there. And so I'm going to do one of two things here. I'm only going to use noble gas configuration because Lord knows we don't want to do all the 1s2, 2s2, or whatever. So I'm going to show you two examples. I'm going to show you one where you take the F block and you're completely using all of them, and then I'm going to show you where you excuse me, where you have to stop somewhere in the F block. So we're going to start out with tungsten, which is 1, 2, 3, 4. Tungsten is in 6th period, 4th spot, right here. Okay? So this is where tungsten is. And so I know that it's going to end in 5d4. Okay? And the noble gas that comes before it is right here, which is xenon. So it's going to be, and this is tungsten. So it's going to be xenon. Okay? And then it's going to be, we're going to probably have to rewrite this, 6s2. And then I get to this pot right here. But remember, these fit in right here and right here. Okay, so I'm going to have to go down here and I'm going to have to grab my 4F. So I'm going to say 4F, 14, and then I'm going to come back up here and do 5D4. And so rearranging that to keep them all in order would be 4F, 14, 5D4, 6S2. Okay, so that's how you would do that. But let's say we are going to stop in the F block, okay? So let's do uranium, which is right here, okay? So I know that it's going to, uranium is going to end in 5F3. 5F3 is uranium, okay? And the one that's going to come before that, of course, is this noble gas, which is radon. So this is uranium. So it's going to end radon. And then after radon comes 7s2. But because this fits in right here, I have to grab that 6d1. And then I go down here and do 5f3. And then, of course, rearranging would be 5f3, 6d1, 7s2, putting them in order of energy levels. Okay, so the difference is if I'm stopping in the F block or if I'm just grabbing all of the F blocks. If I'm just grabbing all of the F blocks, in this case, I go ahead and I do those before the 5D because because I need to end in 5D4, which is after this D1. So what I would not do is 5D1, F4, 14, and then 5D3. I would keep my D's together. But in the second case, because I'm stopping down here, I only need to grab this one right here. Okay? All right. So let's go on and do some ions just real quick, and then that's where we're going to stop the lesson because I know it's getting kind of long, but it takes a lot to explain. So here we have the electron configuration for simple ions, and we're just going to use the noble gas core method. But I'm going to write them out first so you can see it. Okay? And so in this case, we have fluorine, which is a -1. So normally fluorine has 9 electrons, but I've added this one, so now it's going to have 10 electrons. So it's going to be 1s2, 2s2, 2p6, which would be neon. Okay? In the case of calcium, calcium normally has 20 electrons, but it's a +2, means it lost 2. So it's going to have 18 electrons, which would be 1s2, 2s2, 2p6, 3s2, 3p6, which would be argon. So do you see how that works? All right, and then let's go with aluminum. Aluminum normally has 13. +3 means it lost 3 electrons, so now it's 10 electrons, so it's going to be neon. And we will find in the next unit that this is something that's called isoelectronic, meaning it has the same electron configuration as each other. That doesn't mean they become neon, they don't become argon, because they still have the same number of protons in their nucleus. They're just an ion. But that is something you need to recognize as something that's isoelectronic. And I believe that is, yeah, that's where I want to stop. All right, thank you.